participants. I am really glad and rather honored to be with this august audience in making a presentation on fundamentals of neural networks. The topic given to me by the organizers has taken me back almost about 20 years. Somewhere around 92, 93, 94, around those days, I used to work at University of Roorkee as a full-time scholar in trying to understand fundamentals of neural networks, as this was my topic for application of the same with something that can impact the community. My supervisors were not one, it is two, and both of them were trying to push me towards making something that is impactful rather than trying to produce as is needed now, unfortunately, because of various other matters. It is needed that we need to publish papers and all, but originally the paper publications, projects, all these things are supposed to contribute, and the contributions are to the society back, because society has made us what we are today. So let us give it back to the society. That is the concept with which all these schemes have come up in the government of India, government of UAE, or wherever it is in the world. A lot of funding agencies, they are basically for ensuring us to give us back. They are giving us opportunities to ensure us to give us back. However, without digressing much, I would like to take you through the topic of the day. In fact, the fundamental challenge that I faced with neural networks, especially to apply it to something which impacts the community. It was not easy for me to understand. Why is it that I must think about an artificial neural network? Why can't, what is the significance of artificial neural networks? Where should I apply this? What are the specific cases of field problems where these are more applicable? Of course, nothing can beat a human brain. It is not me who says this. Literature says this. With all advancements that we are talking about today, to the extent that I know, we were successful to have come out with a model that truly represents the brain of a fly. Brain of a fly. This is what our research advancements have brought in. Nothing beyond that as of today. A lot of challenges even to come up to this level. To go beyond, we are being challenged by the computer technological innovations, where you require parallel processing concepts to come in. It's not easy. First of all, you should have some platform where you can really implement the parallel processing in real time. The specific problems on which, if at all anybody is planning towards working using neural networks. To my limited experience of working with this neural networks as part of my research for about more than a decade, is that many a times you can understand one reflex of a neural network that every individual, every one of us have. In fact, we name it as something called as a sixth sense. Yeah, based on whatever inputs the mind has taken, the neural network in our brain has taken, some kind of output is delivered in spite of the fact that we have not seen this pattern before. We have not seen this kind of inputs before. We have our own reflex, and that reflex that comes out of us is because of the sixth sense that we call it in very, very loose terms. Many of the aspects of the neural network concepts come from human biology. In fact, psychologists worked a lot, psychiatrists worked a lot. After that, we have got a number of computer specialists trying to give us some hardware, technological innovations that will support implementation of neural networks in practice, which we call them today as artificial neural networks. Artificial intelligence is another aspect, which is a big gamut developed around neural network and complementing with other concepts like deep learning, machine learning. A lot of other concepts have taken birth beyond the neural networks era. So let me take you through my slides first, then I will try to share some of my experiences. My presentation is based on these specific points. A brief introduction. What is a biological neuron? What are the key features? What are the processing elements, key features? What are some historical landmarks? Where and how, there is a spell mistake there, where and how neural networks are used? What are the common neural network architectures you come up with? I'm trying to summarize a lot of things in a short presentation of 90 minutes. To give a glimpse of what is the state of the art today, I come out with a research article, not mine, but it is available in literature. I can give you the reference, you can browse through and you can go through that. But I would like to present that as a case study as applied to your interface, brain-computer interface, how this is coming up with. Let me commence the brief introduction on this. Because the FDP is on brain-computer interface applications of artificial intelligence, let us start with what is the significance of this topic. They have brain-computer interfaces have shown great prospects as real-time bidirectional links between living brains and actuators. Living brains and actuators, these are the two key words. And you should establish a real-time bidirectional link, not as easy challenge there. Artificial intelligence, which can advance the analysis and decoding of neural activity. This concept of artificial intelligence has turbocharged this field of brain-computer interface. Some classification algorithms for EEG-based BCI systems are like adaptive classifiers, tensor classifiers, transfer learning approaches, and deep learning. There are several techniques that came up, and in fact, many of them have their roots in neural networks. A brain-computer interface is a computer-based system that acquires brain signals, analyzes them, translates them into commands that are relayed to an output device to carry out a desired action. A plethora of activities in the brain-computer interface is in this sentence. First, it has to acquire the brain signals. The interface has to analyze the signals that have been acquired, then translate them into certain commands that are relayed to an output device to carry out a desired action. In fact, although this is not practical, but in principle, any type of brain signals could be used to control a brain-computer interface system. Before I go to the biological neuron slide, I would like to understand the significance of neural networks at this juncture applied to this topic. As I told you in the beginning, what I called it as sixth sense in loose terms. Where from I am getting it? Many of the von Neumann architectures that you find in computers, they always try to provide answers to a deterministic definitive equation. For example, outcome is equal to A plus B plus C. If A, B, C, all the three elements are then there, then only outcome will come. Without that, von Neumann computers cannot give an answer. That architecture cannot give an answer. But brain has an architecture which is different from von Neumann architecture, where out of A, B, and C to give an outcome, even if you do not have all the three, B is not there. Only A and C are available. Still, a reasonable outcome can be given by the brain. That is the beauty of any neural network in reality. How does this happen? What exactly is a neuron doing? What is the basic genesis of neuron? This is where we are going to the next slide. The neuron has especially three fundamental components. Any biological neuron for that matter. I am talking not about an artificial neuron. It is a biological neuron we are talking about. Dendrites, soma, and axon, as has been given here. This is your axon, and this is your dendrite, and you have an axon, dendron, and soma. Soma is this part of it, which I am showing in the figure. Same thing keeps repeating. A number of, I don't know how many, the innumerable number of neurons are there in our brain. In this, so this is simply a small model that came up. Dendrites, it receives, basically these are the extensions to other neuron connections actually. Receive signals or electrical impulses from other neurons via synaptic gaps that get transmitted by means of a chemical process. By scaling the received signal frequency like weights in ANN. Then soma, it is the cell body. This is actually your cell body that sums the incoming signals and fires upon receipt of sufficient input. Something like a simple threshold. That is the model with which they started. Thus transmit signals to other cells via axon. So axon is the one which transmits the signal, synaptic. This dendrites is one which receives the signal, and we have the soma, which is actually trying to sum the incoming signals and fires upon the receipt of sufficient input. Basically, it is a kind of threshold that you are talking about. So the key features are processing element receives n number of signals, many signals. Signals may be modified by a weight at the receiving synapse. The processing element sums the weighted inputs. Under appropriate circumstances, once you have got the sufficient input, that's what I mean, the neuron transmits the signal output. Then the output from a particular neuron may go to many other neurons, the axon branches. Now, the first element that I am talking about in the key features is giving us application part. The processing element receives many. How many? So once the signals that you receive are voluminous, the signals that you are receiving are voluminous, it qualifies that you should think about the neural network. This is first qualification as when should I go think about a neural network. The processing element receives many signals. So n number of signals, many as possible. Not just a couple of signals or 2, 3, no, it's many as possible. So innumerable number of signals when they receive. Basically, inputs are to be too many. They have to be too many for one to think about using, because that is exactly where you need to really identify the signal part, whether it is data or information. It can be anything. Data is what you have to look at when you receive a signal, but when you interpret it in a context, it becomes information for you. So when the data or the information that you have is voluminous, yes, this is one element which will make you to qualify to think about, shall we think about an artificial neural network? And the modification of signals are done by the weight. So this is where exactly your intelligence lies. The intelligence that you are talking about, we are modeling somewhere through the weights. A weighted sum is delivered as an output. This is your final decision that is coming out in an application orientation when you look at it. Although basically we are talking about a simple element here, but we are talking about a simple processing element here. We're talking about its application going there. Now, the question of under appropriate circumstances, this is where exactly we are talking about the threshold reaching scenario has to be built. So it is not that every time a neuron transmits a signal output. So there has to be something which should drive it, and that driving to start with is a simple threshold. And then of course people have modified and then modeled it into different things. The output from a particular neuron may go to other neurons, or not just one, but it may be a lot of branches. Maybe. Note that the information processing is local in every neuron and it is parallel. In every cell, if you have a million cells, every cell parallelly processes. Look at the limitation of the computer technology, not so easy. Chemical reactions is the toughest challenge. Biological and chemical reactions are the toughest challenges neural networks face to process. They are not easier. They are much more faster, much more intense, much more in terms of the volume, even beyond a nuclear fusion or fission kind of reactions that take place. Chemical and biological reactions are actually those which are actually making you to come out with an output. So the information processing is local. When you say it's just within a small cell, every cell has a local processing done, and then a sum of that weighted sum has to come out. Now, distributed memory, long-term memory in neuron synapses weight, short-term memory correspond to the signals sent by the neurons. So the signals that are sent is short-term memory. Those weights that got developed becomes the long-term memory here. So by experience, as you try to have more and more experiences, the synapse strength gets modified. Like as much as an experienced doctor can diagnose a patient more accurately than others. So more experience, the synapse strength may be modified. So neurotransmitters for synapses may be excitatory or inhibitory. This is an important component at the system level, the fault tolerance part. Recognizing signals different from the signals seen before. This is exactly where I'm talking about ability of an output, irrespective of all the inputs that you wanted, like the example that I gave, output equal to A plus B plus C plus D plus whatever it is. Not all the inputs are required. Even otherwise also, recognizing signals different from the signals seen before, which is not part of this, but still it will be able to deliver. Continue to learn in spite of continuous loss or damage of neurons as other neurons take over damaged cell functions. So even if some of the cell functions are damaged, still we should be able to have a reasonable output that comes out. This happens even in reality also. Many of the older, they may have reflexes slowed down, or there are few things which they still do have the abilities, any older person for that matter. So the same thing is what we are talking about. Fault tolerance is going to be high level in such processing element. This is one of the features. Certain historical landmarks, let us look into. There are a number of things that happened in the history. A combination of progress in experimental work with biological neural systems, computer modeling of biological neural systems. This is another topic which has gone through the history. The development of mathematical models and their applications to the problems in a variety of fields. Hardware implementation of these models. These are the various things that have taken place. Of course, some of the very important historical landmarks are, these are some of the historical landmarks. So 1940s, we have seen the MP neurons, then Hebb learning. 50s and 60s, the first golden age of neural network where perceptron and Adeline took over. 70s, you find the quiet years, basically not much, but they were working mostly on architectural aspects and going into Cohen, Anderson, Grasberg, the Carpenter. These are the people who have contributed a lot for neural networks based on fundamentals developed till date. 1980s, again the renewed enthusiasm came up. That is when you find the backpropagation networks, off-field networks, neocognitive networks, Boltzmann machines, leading towards finally hardware implementation. It is a simple journey that neural networks has taken. Where and how these neural networks are used? A number of areas: signal processing, control, pattern recognition, medicine, speech production, speech recognition, business, variety of places. Typically, the architectures, if you try to look at either single or multi or competitive layer you have, nets. These are the typical architectures you find in neural networks. Setting up the weights, either supervised training or unsupervised training or fixed weights. Common activation functions happen to be identity function, binary step function, binary sigmoid, bipolar sigmoid. These are certain common activation functions being employed. So I'm just touching the basic fundamental aspects of various neural network architectures here. This is a simple single layer example that is shown in this case. It is a pattern classification and pattern association nets using Hebb or delta rule. It is not del rule, delta rule. So here we have the set of inputs and a set of outputs, then we have a weight. So basically this is where exactly your intelligence lies. Then we will think about the multi-layer to perform nonlinear mapping. This could be mostly used for linear. This you have basically for nonlinear mapping, n-dimensional space of input vectors. We call it as n-tuples to an m-dimensional output space. Your backpropagation network is one such example. Generalized delta rule, we use it for weight adjustments. The rule that I am talking about is basically how do they adjust. Then we have a competitive layer. Interconnections have weights, typically are not shown here, but it is minus sigma for m nodes. So they just try to compete and you'll have a winner and winner take all. Winner neuron only on. So out of these neurons, which is the winner, that is being decided by these interconnections and the associated training that you are imparting, and you are going to speak during training which is winner, what kind of a weight adjustments it should take place for an unknown pattern. Whichever neuron gets wins over the others, then they are going to take over the entire network. So this is where exactly the training or setting weights very, very, very challenging task for one who is trying to design neural networks. The challenging task is how do you prepare the training patterns? How do you prepare the test patterns? In mathematics, we talk about orthogonality of the training patterns. In fact, a lot of mathematics can be involved here. When you talk about orthogonality of training patterns, one training pattern and its associated output, another training pattern and its associated. When you try to compare, there should not be a commonality. It should be exactly different, altogether a different dimensional pattern you should try to bring in. So the intersection should be to the extent possible 0. So orthogonality has to be maintained with respect to the designing of training sets to challenge the neural network, whether it is whatever architectures that you talk about here you use, but you must be in a position to design. If you are trying to look at the supervised training networks, then in this case, present a sequence of training vectors. Designing of training vectors, you should be very, very careful in trying to bring in orthogonality in each vector, between the vectors or patterns, each with an associated target output, so that the weights are adjusted according to the learning algorithm. Now, algorithm is another area where people work a lot. Most of us, the challenge is that we use either existing algorithms or we come up with our own algorithms for these learning algorithms. In fact, still a lot of research is going on in this area. Classification of patterns via a single layer or multi-layer net. Usually, pattern classification is done via this kind of networks. Pattern association type of problems you use, in which it is just output is just a yes or no. It is associated with a particular pattern, yes, otherwise no, kind of an output. So auto or hetero-associative memory nets are for example, feed-forward and recurrent or neural networks are quite famous examples here. There are other forms of employed under supervised training. You can use LVQs and counter-propagation networks. Coming to the unsupervised training, there are self-organizing maps. A neural network which organizes itself as it goes to. So there is no question of separate training being done. It trains itself in the first initial patterns, and later on it gets experienced by itself. If you take a doctor who is in an intern going to the hospital, to face his first OP, outpatient ward, obviously it is a self-organizing map in his mind, because he's trying to get experienced with the real life patients there. And he starts learning from there, and hence there is no supervision, because he's now completed his 5 years of learning, and then he goes on to the intern to sit probably in an outpatient ward or to directly work on the new patients who are on the hospital. The self-organizing map basically is to start learning slowly from case to case. Without use of training data, we will try to have this kind of self-organizing neural nets. Specify what type of a typical member of each group looks like, or which group each vector belongs. Basically, when it comes to the diagnosis in case of brain diseases or biomedical diseases, it tries to classify itself through self-organizing map. They call it as differential diagnosis in medicinal education. When they try to give education in medicine, they make doctors learn what is called as differential diagnosis. So a patient presents himself to a doctor, let us say. From his physiological model that he has in his mind, he tries to look up the human subject. He takes all the symptoms and tries to diagnose first into a set of put this symptoms map to a particular disease or others. So they try to distinguish which is more likely, less likely. So this kind of a approach is taken up in this kind of unsupervised training. Thereby, in fact, if you look at some of the real examples, real world examples, if you see, if you try to link it with unsupervised learning, for example, if you take a doctor who tries to prescribe a medication and says, I am putting you under observation for a couple of days. I'll give you this medication, I keep observing, and then I'll change the medicines. Basically, he's trying to use the differential diagnosis technique there in trying to identify the disease. So that is where exactly you find this unsupervised training, because many times you do not know whether you are a part of the same, yes, whether you are part of the same, known diseases or unknown diseases, we do not know when you are actually trying to look at the patient. So unsupervised training helps patients, whatever be the kind of known diseases that they have, if it is falling into one of those patterns, his treatment, which is given for a couple of days and patient being under observation, is responding towards betterment, then that means more confirming that the diagnosis looks to be okay. Otherwise, we'll change the course and then tries to take him to the other. So it is a unsupervised learning or training that is going on in the initial part. Once diagnosis is done, we can try to go towards a definitive answer. That's where exactly you can see here a typical member of which group looks like or to which group each vector belongs. That is where exactly he is trying to identify in this unsupervised. Then a sequence of input vectors are provided, but no target vectors are specified here. You see this. The net modifies the weights so that most of the similar vectors are assigned to the same output cluster. So it is again a cluster, a set of diseases. Probably it may be either this or this or this. I'm not sure. So we have to diagnose between them and then try to arrive at what could be the kind of disease. This is where unsupervised training helps. Some examples of this is coherent self-organizing maps, adaptive resonance theory based. These are some of the examples that we find in practice. Coming to the fixed weight training method, the net is tasked to find a nearly optimal solution. Typically, in constrained optimization problems. So you have a lot of constraints within which you have to find a solution, an optimal solution. You can't say this is wrong or this is right. Yeah, everything is right and everything is wrong. But there is something which is optimally the best kind of scenarios you find in practice. That is where exactly your fixed weights. The net is tasked to find a nearly optimal solution. Typically in a constrained optimization problem, where difficulty for traditional nets are due to conflicting constraints. So a conflicting constraints that you have in the very traditional thing that is overcome by these fixed nets. Not all constraints can be satisfied simultaneously. Many a times the training sessions may go too long. So they try to fix weights, and these weights are considered to be those which are nearly optimal. Sometimes empirically you may arrive at the weights. Weights in such cases are set to represent the constraints and the quantity to be maximized or minimized. That's all. It's the kind of criteria you are trying to come up with. For example, Boltzmann machine. Without learning and continuous half-field nets are used for such problems. Fixed weights are also employed in contrast enhancing nets also. I want to enhance the contrast of an image. Most of the times the brain signals that you are trying to take up, sometimes the noise, the image processing aspects where you need to enhance the contrast, you use such nets. Common activation functions. These are some of the common activation functions to come up with. These are quite fundamental activation functions that we are talking about. We are not doing complicated advanced stages because I am tasked with developing or trying to introduce to the fundamentals of just using some common activation functions. Most commonly, this is the sigmoidal function which we normally use, either this or this. These are the two things which are being used. Very rarely we go for these kind of functions. However, if the problem is linear, you know that we can fix a linear kind of a function, we will go with this. Otherwise, we go for most commonly you find these kind of activation functions in many biological applications I have seen. So till now, what we have discussed, if you go backwards once and then look at the aspects that are coming up, these are certain fundamentals about architectures, some fundamentals about training mechanisms, some fundamentals on common activation functions. So once these are the three basic constituents that you have for every fundamentals of a neural network, usually. Now we are trying towards the case study. Brain-inspired spiking neural network. The reference of this I have already given somewhere in the last, in references you find this. This is the reference that I am giving. You can go back and refer to that. I am just trying to present a case study here. It's an architecture. Its architecture can learn and reveal deep in time-space functional and structural patterns from spatio-temporal data. The architecture itself can learn these things. The brain-inspired spiking. That's what we are trying to look at here in this. These patterns can be represented as deep knowledge. Again, the concepts of deep learning comes up in this to start with, in a practical sense, in the form of deep spatio-temporal rules. This is actually a theoretical framework, and its experimental validation on deep knowledge extraction and representation using SNN has been presented in this particular paper. It is worth going through as a case study by all the participants. The proposed methodology was applied in a case study to extract deep knowledge of the functional and structural organization of the brain's neural network during the execution of a grasp and lift task. They just use these two tasks. That's why I said it is a simple case study. And the result is that the BCI successfully extracted the neural trajectories that represent the dorsal and ventral visual information processing streams, as well as its connection to the motor cortex in the brain. Deep spatio-temporal rules on functional and structural interaction of distinct brain areas were also then used for event prediction. These are the two fundamental results that this case study comes out with. The computational framework can also be used, as used in this case, for unveiling the topological patterns of the brain, and such knowledge can be effectively used to enhance the state of the art in BCI. These are the claims that comes out from the authors. Quite an interesting paper I found that is connected to this particular FDP. I have provided a number of references for each of the part that I have dealt with. History, technical, non-technical, as well as the applications. These are various references you can look at. Basically, I'm not made them because I'm dealing with fundamentals. Most of them come from 89, 88. Pardon for this small typo errors here. 90. These are the basic. It comes from the neural networks for signal processing. There is a. These are the textbooks that you are available also. So one can go through these references with regard to the fundamentals of the neural networks. I'll be glad if you have any questions, and session is open now for questions. My presentation more or less I conclude now, although I have taken very less time than what has been allotted to me, around 90 minutes or so, which is not required. So it's simple fundamentals only we are dealing with. But I don't want to diverge myself from the basic topic that has been assigned to me. And neural networks have advanced a lot of experiences. You can share or you can ask any questions, will be most welcome. The remaining session, I leave it to the participants to open or throw some questions, which I can probably address or answer. Thank you.
Thank you. Thank you so much, Dr. Gunturu sir, for your valuable information on the fundamentals of neural networks. I hope the participants gain the fundamentals information. So now the floor is open for all the participants. Please ask if you have any questions to Professor Gunturu, sir.
Yeah.
Once again, I request participants, please take this opportunity to ask any questions on artificial neural networks. So, Professor Gunturu.
Yeah,
So
Dr.
If you may, can
Lakshman, I can make the participants to write to me if in case they have any interactions to be made through email also. I have just flashed my email ID. It is up to them to interact with me over emails too. Okay.
Oh, okay. Thank you, sir. So, participants, sir has put up his email ID over the slides. Please take that information. And if you want to write, if you want to interact with sir on more on this, you can write to sir. And if you have any questions right now, you can also use chat option to type up. And sir, Dr. Gunturu, sir, if you hello, can I ask you a simple question, sir?
Please go ahead.
Okay, sir, I'm not from this neural network area, or I just know the basics. I have a simple, how can I relate this? I mean, how can you relate this neural network to, let's say, VLSI? Is there any a common area that we can sit on or work on with neurons and VLSI in terms of circuit making? I just want to have a broad perspective on this.
See, Dr. Lakshman, it's a nice question, and I would like to tell you there are certain areas where in VLSI it can be applied. Especially you have an area in the integration. While you are trying to bring down the scale of integration, enhance the scale of integration, you need a lot of mapping of various areas of the components. So it has been used in a number of places and in various layers. They are actually trying to, not audible, sir, not audible. Sir, slides change. Chart box I am seeing.
Okay, sir.
So it can be used in a number of ways, especially when you are trying to use integration, scale of integration. That is the area where the neural networks are employed to map how optimally we can try to make use of this size available on the silicon. This is where I have seen a number of algorithms that have been used by neural networks in VLSI domain. I know some researchers also who worked in this area, who are working also currently at NIT Warangal as well as NIT Durgapur and at VNIT Nagpur. All the three places, there are people who are working in this area. So I can be of help to you in case you have any such ideas there.
Thank you so much, sir. Participants, please use this opportunity to ask any questions. And for your information, I have already put up Dr. Gunturu's email ID in the chat box. You can use that, store it for future references, and you may write to sir at any time.
Dr. Lakshman, for the benefit of the participants, I also would like to share a textbook which is available online on fundamentals of neural networks. So that can be given to the participants so that they can also refer to that, which I found it very informative on fundamentals.
Thank you so much.
I'll share it with the organizers as well as you, Dr. Lakshman, over a meet.
Sure. Okay, sir. We'll make sure it reaches all the participants so that they can be greatly benefited from them.
As part of the course material, you can include them for them to make use of it.
Sure, sir.
Yeah.
Participants, please.
In fact, there are a number of softwares that have come out for making every participant to try on the fundamentals of the neural network. Also, they want to improve their understanding and its application to various domains. There is one software which I can say out of the hat, and I used that software also. Once in a while. Of course, MATLAB has come with a lot of packages under neural network, no doubt. It is a very popular one. Other than that, you have ExploreNet, EXPLORE. I am just trying to write it in the chart box. ExploreNet. This is one software I have seen number of times. People can use this. Like, it is very, very simple software on learning the fundamentals. We started using this software the beginning of my journey towards neural networks. Believe me, it gives a variety of neural networks, how to apply, where to use, and all. There is also another resource which is a textbook on PC tools on neural networks. Exact details of this textbook, I can, if anybody wants, I can share it by an email, because right now I don't have it, but I can definitely share PC tools on neural networks. How to use tools of the PC on neural networks. This will again, these simple PC tools can be used to explore neural network fundamentals to understand them. Another resource that one can, somebody is really keen to work on it, we can try to do that. A lot of things are available. Pramod Kumar at cbr.ac.in. I have noted down. Probably he requires the textbook details. I'll try to pass it on. I've seen it in the chat box. Your request is noted, and we will try to mail it to you, the details. I am observing the chat box for any questions or any interaction will be quite. I'm happy to be with you. As well, we can correspond over emails too. If you think in future you may get some doubts, some clarification, some guidance, I'm available.
Participants, please use this opportunity to ask any questions.
Yeah, there is a question I'm seeing. Archana PS, how best is neural network for machine learning and IoT? In fact, many of the machine learning and IoT areas explore neural networks a lot. Only thing is the direction is has not been picked up much as it is to be. But machine learning, definitely yes. A lot of applications are available, and neural networks can be employed as part of machine learning. In fact, it is hidden these days. Earlier days, we used to write programs on neural networks, layers, try to do our own programming and try to do our own training, like trying to create sets and all. I used to myself sit and write these programs using C++ kind of languages, and then apply it and try to work it on non-human computers. Naturally, a parallel processing element, we need to implement using a non-human architecture. You can see the challenges of those days that we face. But today, machine learning techniques have brought in, there are a number of architectural aspects like pipeline architectures. A number of things have come up in architectural microprocessor architectures also that facilitate neural networks in machine learning, that facilitate neural network time. Tremendous potential to have in ML as well as in IoT applications. Most recently, I can probably share one experience with respect to this question of Archana PS. For I am myself involved in the past 1.5 to 2 years in one particular field application, which is about empowering remote and tribal areas. Why not we try to empower them with medicinal facilities, diagnostic facilities? That is where we started using IoT devices. Why not we think about IoT devices? There, we try to put the intelligence in the cloud. IoT devices will be the actuators or sensors. That is how I used to use the IoT devices. And we are actually developed this model of putting cloud to be the intelligence in the cloud. Actuators and sensors will be on the ground using IoT devices, link them up with the cloud. This concept we visualized and we try to put them into an entrepreneurial application also, and we try to present it to the IEEE connect the unconnected, because we want the rural population to get medical facilities. So we tried this concept, and believe me, the Future Networks Initiative of IEEE has made this particular idea that we have coined as a concept as a nice business model also. So we are now trying to bring up something through an entrepreneurial exercise too. It's really a wonderful application of IoT with cloud, with learning there. Thank you for the informative lecture. Thanks a lot for. So, Dr. Lakshman, can we close it
Yes,
for the
sir.
time being?
Yes, sir. Yes, sir.
If there is any questions, yes, most welcome. They can come
Sure, sure.
by email or and I can respond. Okay.
Participants, if you have any questions, you can use Dr. Gunturu's email, or you can even email the organizers. We will help you to connect both Dr. Gunturu sir and yourself, and you can have wonderful sessions and information exchanges between yourself and sir for your respective colleagues. With this, again, sir, Dr. Gunturu sir, thank you so much for
Thank
coming to this online virtual FTP and sharing the valuable information and fundamentals of neural networks. Thanks a lot, sir.
Thank you so much. Thank you. Yeah, kindly share PPTs. This is coming from Archana Priyadarshini. It will be done by the
Sure,
organizers.
sure,
By the organizers.
sure, sure.
Along with a resource textbook, 1 or 2 textbooks also I will try to share with them. That will come to you in the material. Thank you.
Sure, sure. Thanks.
All
Thanks a
the
lot,
best.
sir.
Yes, thank you. Can I leave, Dr. Lakshman?
Yes, sir. Yes, sir.
Thank you.
Thank you, sir. Participants, that is the end of the first session today. So I request all of you to take a quick break, not a quick break, a decent break of half an hour, and come back at 11:45 a.m. for our next lecture on who is going to be Dr. Jude Hemant, sir from Karunya University is going to give a lecture on AI, ML, and CNN applications for biomedical signals. So we will meet at 11:45 participants. Thanks a lot, everyone.
That's the
Welcome back, participants.